right. Hello, world. So last time I think I addressed some, I probably redid 46 because I wanted to explain, like I had gotten stuck at some point, but then after the stream I realized when I did 46, I did it by multiplying by this denominator, and then I just considered what the product of those two series would be, and I was trying to show that the coefficients would vanish above degree n, above, the nth coefficient, but I didn't recognize that it was like the nth finite difference of a polynomial of degree n. Like basically the nth finite difference of z to the n, which would be 0. Well, n plus first difference, I guess I should say. And the way he did it was, let's see. I want to say using some, the way he did it was he recognized, he basically wrote down a recursive relation. He said what fn plus 1 would be in terms of fn. Anyway, after that, 47 through 49 were all differential equations. They weren't too bad. If you're comfortable with this new operator, z ddz, these pretty much all fall out without a lot of work. I mean, 49 uses 48. 48, I just wrote down both sides of this differential equation. Same thing with 47. I really just wrote down both sides and it seemed to pop right out. So that was that. So I'm on 50 today. The next 10 problems, 50 through 60, are in section 4, functional equations and power series. I guess I've never heard this this term before, functional equation. It looks like he's just saying an equation that involves functions. Because these are not functionals in the sense of like a linear functional. These are just functions, and they happen to be, it looks like they all have that sort of recursive property again. Like if you plug, say q, like here, this maybe that's what he means by functional in this sense. I would maybe call that recursive. Anyway, so I took a little screenshot of the problems that you can see on the top right here. So I'll try to get through those. First one says our function is f of z is 1 minus qz times 1 minus q squared z, 1 minus q cubed z, etc. for a q that's less than 1. Show that this can be expanded in a power series. And then find the coefficients using this equation. So that's a pretty big hint. And I guess that's what he means by a functional equation. This is clearly like standard terminology that I'm not used to, right? Functional equation. The unknown is an entire function rather than a number or variable. Okay, yeah. Yeah, I just hadn't heard this expression before. Recurrence relations, of course. Periodic functions satisfy a functional equation. Okay. Yeah, I just never heard that term before. All right. So on this first one, supposed to realize, first of all, here is the function. So on. And then let's see if I can, I know I just looked at it, but if we plug in QZ, you basically lose the first term. So we would have to multiply by 1 minus. Yeah, there is no 1 minus z term here, right? So if we plug in QZ into this equation, you get Q squared immediately. You lose this first factor. So that's why we're going to be able to just multiply by this to get the original function back. And there's your functional equation. He basically says we can use this to find the coefficients. Evidently, Fz is the same as some power series. Now, do we have, I guess we could have, I was going to say we could have negative powers of z, right? But no, not really. Not like this. You could maybe have 1 minus z in the denominator. You see what I'm saying? Like if I divide by this, you'll get another expression that looks like f, but is not f. Anyway, this is going from 0 to infinity is what I'm saying. That was the only reason I was babbling about that, just kind of thinking about it. All right. So, I'm sure that it can be written this way and use this to get the coefficients. Well, it stands to reason A naught is 1. Right? We could plug 0 in for z and see that. So f of 0 being 1 tells us A naught. I can't, let's see. I was going to say I'm hesitant to throw z equal 1 in there, but perhaps it's not a problem because the q's are less than 1. Are they strictly less than 1? Yep. All right. So this, is f of 1 0? I see it's an infinite product. I'm just thinking out loud here. F of 1 is this. And I know that q is less than 1. So isn't this, yeah, it's got to be 0. Well, if it's 0, what is f of q? This is always true. So fq is 1 minus q squared fq squared. I mean, it doesn't have to make sense at 1. You know, there could be some radius of convergence that I'm ignoring, but And of course, if I plug in like a power, you get the same kind of statement. Q to the k gives you k plus 1 over here, you know. Does that make sense? If I plug in q squared, you start off with a q cubed. And then I multiply this, and I play. Oh, no, that's correct. That's correct. Of course, it makes sense. So yeah, you can iterate this. Of course, if you just plug in 1, you get what I sort of said here. F of 1 also should give you the first one, right? What if I plug in 1 over q, right? Do I get 0? I'm supposed to get 0. Oh yeah, of course you do. So there's no real problem there. What does that tell you? If you believe that you get 0 here, that doesn't really tell me anything. But for some reason I thought f of 1 would also be 0. So is f of q always 0? I don't see why. Well, again, like, this doesn't have to make sense. What I just wrote down here, there could be a kind of radius of convergence where this makes sense. You know, the function might not exist for a z larger than 1, for instance, in which case this last statement doesn't make any sense. But I thought f of 1 would be 0. Because 1 minus q to the k gets smaller and smaller as k gets large. No, it actually does the opposite. It gets closer to 1. Huh. For some reason I mistook this for q to the k. Okay. Good. That means it's not annihilating. Like, q is not a root. Powers of q are not roots of this function. Which is good. It's not what I expected to see, so yeah, f of 1 is not 0. I must have just mistook what I was looking at here. I was thinking of powers of this, not powers of q. So yeah, q goes to 0. I mean, sorry, q to the k shrinks arbitrarily. But 1 minus that is closer to 1, not closer to 0. So this is kind of indeterminate. I'm not really sure what that is. Yeah, f of 1, it's not clear what that is. But it's probably convergent. I'm a little rusty on showing why this would converge. I've seen this kind of thing a long time ago, but I guess we'll see if I answer this question. We'll see if it's convergent kind of right away, because we'll have a formula for the AKs. All right, so what do you want to do? We knew this relation, and somehow that's going to help me get the AKs. I guess we could start. We could start just writing them out. You could also just expand this, but that's kind of slow. Yeah, I should be able to get just a straight statement about the AKs kind of quickly, right? I'm looking at 50 if it's not clear. So like you can see multiplying by this factor does not alter either the first or second terms of this power series. It finally contributes z squared, so you start to get some involvement of the third term. Still just like this was his hint, was to use this to get the coefficients. So I feel like I ought to be able to get a statement about like an plus 1 in terms of an pretty quickly. Now we know this is true. I'm going to say maybe we know another relation, but we shouldn't need another one. This is what's true. Okay, what if I multiply by z instead? Or what if I just distribute this, you know? Like this minus qz gives you back. So for one thing, wait a minute, maybe I'm wrong about that. Yeah, does the coefficient, yeah, the first coefficient a1, it does look like it involves a bunch of terms, right? Because this q cubed against 1, q cubed z against 1 is going to be changing the coefficient of z. You get itself minus blah. So it seems like every step of the way you're getting a change. Right. For some reason I thought it was z squared, z cubed, but it's not. It's not what it says. Okay. All right. So if we do assume that it's a Taylor series, right, and you use this relation, we're looking at this equals 1 minus qz times this. So if we're a little careful with the distributing here, oops. No, you're right. Q to the k, z to the k, minus qz times this. These all start at 0 and go up forever. Here we get ak, but we increase both of these by 1. So you have no 1, well, you still have a 1 term, but it's been shifted, so it's 1 qz here. So if you want to maybe re-index this, like what happens to the 0 term? It's not constant anymore. Well, okay, let's do it this way instead. Let's go 1 plus 1 to infinity right? And then here's where I'm saying you probably want to re-index this. You could go 1 and up, but you're going to change this to -1. So now these match up except for the AKs. Over here I have 1 plus AK. That's it, right? Yes, so you have AK is AK QK minus. So it looks like AK is Q to the K times 1 minus. Oops. It's not 1, it's AK minus 1, like that. So, for instance, A1 we know is, A0 we know is 1. A1 would then be Q times A1 minus A0. Huh. I wonder if there's a nicer way. I don't think there's going to be a nicer way to express that. This is probably what he wanted. You know, for instance, this is QA1 minus Q, right? So you can solve. Oh, maybe we can actually. You know, we get 1 minus Q equals negative Q, something like this. I'll do another one or two, but like, yeah, could you, I mean, sure, we can solve it. You want to solve it, I guess? Another way to phrase this is that AK times 1 minus Q to the K is equal to negative Q to the K times the previous. So this is a slightly nicer formula. You know, in general, AK is Q to the K over Q to the K minus 1 times the previous coefficient. That's going to be as far as we can take it, I believe. We got 1, then we get this thing. Well, yeah, so for A1 we got Q over Q minus 1 because A0 was 1. Yep. For A2 we're going to get Q squared over Q squared minus 1. However, it's times the previous coefficient, which is this nasty stuff. So you get Q cubed over this product. The sum of these exponents are 3 also. A3 is going to be Q cubed over Q cubed minus 1 times the previous coefficient. All right, okay. We could get, it looks like we can get a sort of closed form thing if you want. This is a factorial, and then downstairs we have a product of, I don't see that cleaning up any more than that. You want to see one more, I suppose? So you start with this, and then you multiply by the previous. So this power you could see is coming from a sum. You know, this power is like n times n plus 1 over 2. So for instance here, n plus 1, n over 2 is 2, and n plus 1 is 5, so you're getting q to the 10. And then downstairs you just have a product of so I was able to get a much nicer closed form formula. Looks like I'm getting, in general, let's put a k here. In general, I'm getting q to the k plus 1 over 2, right? And then downstairs, you could write a product if you want. I don't really see a nice way to write it, but on the kth one, you'll get q to the k minus 1 times all the smaller terms. Q to the k minus 1, all the way down to just q minus 1, like that. You could express it as a product, I suppose, if you want. That explains why q can't be greater than 1. Q can't be 1. If we had allowed q to be 1 in your original function, I would just get this infinite product of 1 minus z to the infinity. That's a bit silly. I guess that only converges for z equal to 1. Does it equal 0 everywhere else? Because it equals 0 at... No, it doesn't. It doesn't. It just doesn't make sense. I wonder, though. Just thinking out loud, if you took product of 1 minus z, there's no dependence here on a variable. It's just 1 minus z. Infinite product of that. I can see at 1, of course, you get 0, but what if you plug in half? Isn't that just half times half times half? Doesn't it, like, it tends to 0. So does this just always equal 0? Obviously, we have a problem once you get bigger. So I'm only talking about when z is, say, less than or equal to 1. Once you plug in 2, we have issues. It's not convergent anymore. But anyway, I'm just daydreaming. All right, so this has got to be the answer for 50. That's an interesting power series. I was curious if it had converged, right? Somehow I don't feel any better about it. I was kind of curious if the sum of the AKs was going to be finite. Like is f of 1 convergent? Obviously yes, right? But is that true? If you took I don't really want to take a ratio test of this, but if we did, you know, ak plus 1 over ak, you get an extra, this guy downstairs. Well, this one cancels, so that's not upstairs. You just get an extra one of these. And then upstairs you have an extra, you have k plus 1, k plus 2. Over 2, whereas downstairs you'd have just a single one of these, right? And then the rest of these terms canceled. There was, you know, k factors upstairs and k plus 1 factors downstairs, but they all cancel except for this one. And now, if I look at this difference, so we're subtracting k plus 1 by k. What we're left with is what we're left with is 2 times that, which cancels, which gives you q to the k plus 1. Right? Q is less than 1, of course. So this is negative downstairs. We get 1 minus 1 over this. Should we just get something bigger than 1? Yeah, right? It's hard for me to see because this is a tiny fraction. So when you subtract 1 from it, like say we had a tenth over a tenth minus 1, right? That's a negative a ninth or something? Or 9/10 is what I meant to say. Negative 10/9. It is bigger than 1. Huh. Is this thing really divergent at z equal 1? For some reason I had hoped this was convergent, but I guess I'm just wrong. Let me just double check this. I'm using this formula with a ratio test just to see what happened. You get, of course, an extra this factor of this form on the bottom. The rest of them cancel. Yep. And then at k plus 1, you get this term, but shifted up 1, so it's k plus 1, k plus 2. If you multiply by k, that agrees with what we see downstairs. So I'm subtracting that. So that's gone, and you just get 2 over 2, you get k plus 1. So I'm pretty confident about this as the ratio. And then apparently that's bigger than 1. I'm a little too confused to see it for some reason. Q we know is a fraction, so if you want you can negate this to maybe make it easier to read. But for some reason I thought this was greater than 1 in magnitude. Just because oh, no it's not. 9/10. Yeah, it's 1/9. That's what I said first. I got negative 1/9 for my silly example here. I just did it too quick. Yeah, it's 1/9, right? So it is convergent. Okay, good. Good. If you really want to do the ratio test, there should be a z in here, so it might help us to see like what values of z this is even defined for. So we'd have an absolute z next to this, you'd be saying this is convergent when this is less than 1. In other words, when z is less than the reciprocal of this. That is a little easier to read. Yeah, I don't love it. Doesn't that just say that it converges everywhere? And also this doesn't matter because this is generally in absolute values. Um, right? It's saying this is less than the limit of, you know, like that. Converges when this happens. Um, but does this not blow up? Like this first term is infinity for any q less than 1. So I'm getting an infinite radius of convergence. That's good news. I mean, yeah, what else do you want to see? If q was 1, it doesn't converge. This is the second time we've seen that. Because I was thinking about this earlier. But I sort of thought, like, shouldn't I be able to talk about the number 1/10 to infinity or 9/10 to infinity? Shouldn't it be clear that these numbers are 0? This is a more basic question. Like, this is probably a pretty simple real analysis question, but yeah, I mean, those are 0, obviously, right? There's not much to say. So why wouldn't it, let's see, because if you buy this, when q equals 1, maybe I just shouldn't trust this computation when q equals 1, right? Because it doesn't make any sense. These factors didn't make any sense. These coefficients, excuse me, make no sense at all when when q equals 1. So maybe don't worry about that. But yeah, it seems like it would be telling me the radius of convergence is 0, and I'm saying that's not true. It's more like 1. Of course, it's identically 0. Anyway, this was kind of a cute thought. But it's just leading me to stuff like this, which either by convention is 0 or, I mean, right? I'm saying if you give me an epsilon and you give me a number a fraction, then, well, I'm not talking about the limit of the power. Yeah, I am. Q to the k, again and again and again. Okay, fine. I'm saying that this goes to 0. Like there exists a power such that 1 over q to the n is arbitrarily small. That seems like a given. Yep. So yeah, this is not a very useful function. All right, well, I'll stop worrying about q being 1 because they told me not to anyway. I was just daydreaming for a second. So we got these coefficients for 50. Maybe we'll take a quick look at the answer for 50. We get this relation that is indeed, did I have an extra qn? I got this. If you want to multiply by k minus 1, that's fine. So we got the same answer. But this previous line, oh yeah. That's what I said here. Okay, good. Huh. -1, and then these are the same. This one. Oh, there it is. This is that. It's obviously the same. I'm just, oops. And -1 times q to the k, yeah, equals ak times, oh, I misread it. I see. Q to the k -1. Yeah, good. That's q to the n -1. For some reason, I thought I put a -1 in the exponent. See, my sloppy penmanship is keeping me on my toes. So, all right. So that's 50. 50 was just, take this function, this infinite product of like 1 minus a power of q times z, and we showed that you can express it as a power series. The coefficients end up looking like this, which I would not have guessed just from glancing at it, but once you have this recursive, or I guess I should say functional equation, you kind of quickly get this for the coefficients if you just write down what it would mean to be a power series for f. So here's the power series f, here's the power series of f of qz. There's our little multiplier guy. Anyway, when you jot that down and expand it, you just get these coefficients. And when you iterate that, or actually you can just solve it immediately. You'll get this, right? And then when you sort of iterate that, you'll see a pattern. Of course, I'm assuming that a0 is 1, but that's because if you expanded this infinite product, the coefficient is 1. Or what else can we do? What if you plug in 0 here? You get f0 equals f0. That doesn't really help us. And fractions give us 0, which is not what I wanted. Well, not all fractions give us 0, just reciprocals of powers of q. It's a little strange though, isn't it? Was that just 1 over q, or was that it should be every power, shouldn't it? Like if I look at 1 over q squared, you get, no, you don't. You don't get 0 anymore. Okay, good. I was going to say, it would be weird if we had a subsequence tending to 0, but somehow it still gives you 1. Yeah. But 1 over q is 0, so I do get 0. So like here you get 1 over q, but then there you get f of 1 over q, which I know is 0. And like, it's going to keep happening. So we do have a subsequence. I'm saying that this is 0. Oh, that's not going to 0, you dick. 1 over q is going to infinity. Yeah, okay. We needed to go the other way. So yeah, this gives you this. I'm just what I'm daydreaming right now is like, how do you prove this? I had already justified it to myself because the coefficient, or the constant coefficient in this series, when the power of z is 0, obviously it's 1, right? It's 1 times 1 times 1 times 1. So how could it be anything but 1? So there's nothing further to say. I'm done with this problem. But I was just wondering if there's another way to prove that from this functional equation, right? And so if you plug in, this is our functional equation again. But if you look at larger powers of q, because those are tending to 0 as k gets big, right? sorry, q is forced to be less than 1. Anyway, those are turning to 0. If you take a positive power of k, so now I'm like, well, what happens to, what happens to this subsequence? It's clearly going to 1, right? Is that going to be obvious? Let's see. I don't know. This goes to 0, so this is like a 1. Yeah, it is going to be obvious, right? You're getting that this ratio is 1. So yeah. This is even closer to 0, to f of 0. Anyway, I'm imagining that this proves that this happens. It is continuous. So we've found a quantity whose ratio is 1. That doesn't prove anything. Yeah, for some reason I thought it would just jump right out here. Well, yeah, all this tells me is that it equals itself. It doesn't tell me that f of 0 is 1, it just tells me it's constant. Yeah, so you don't get it from this functional equation. Really? Well, okay. What about just any, not this particular sequence, but any sequence going to 0? You'll get 0 is, it's going to say the same thing. It's the same result. Yeah, you can't get this from this functional equation. I only got it from the original statement, I only knew that it was 1 because because obviously, because it was kind of hand wavy. But when you multiply all these out, the constant term is 1. Any other term will involve, like this times anything will be z, will involve z. So we only care about the first term. This times the other stuff. I mean, I guess we could maybe argue that multiplying by something like this is still continuous. And I could take like a partial product, and you can see that for every partial product, the coefficient is 1. I don't know, I'll have to think about that. You see what I'm saying? If I define Fn as the partial product of this, we notice that it's 1 plus other stuff. And of course, it tends to our function. And anyway, is this enough to demonstrate that f of 0 is 1? But I'm going to move on. Let me just start with a fresh piece of paper here. So let's look at 51. Let f be the same function. Find the coefficients of the reciprocal. So suppose this is now a power series starting at 0. Yeah, find these coefficients of b. If we need the old one for f. We'll just call f, ak. Like we're looking at this. And we're saying that this is equal to our new power series. Is there like a general... I don't remember a general formula for that, but that doesn't mean there isn't one. Okay, so that's a separate question. That's actually not really what he's telling me to do. But that was just my first thought, is like, is there a general formula for such a question? That's not actually what he's telling me to do. He's saying we have a function. This is explicitly for our function that does, is it plus or minus? I can't remember anymore. Minus. He's saying explicitly for this function, which is a simpler question, right? This is a special case. And this function satisfies, if you plug in qz, it kind of scales. So you lose this first term, and so when you remultiply by it, you get fz back. So we know that our function does this, which means we know that our reciprocal does something similar. You could do this maybe. So if you call this function g, it satisfies that g of z is, let's just move this over here, that'd be a nicer way to phrase it, right? 1 minus qz times g gives you back g of qz is our new, I guess this is different than the previous one, right? So this is the way you'd phrase it for the reciprocal function. But most power series don't have this functional equation. Actually, don't they? Don't they? If you had a general power series and you scale it by z, this is a0, a1, well, starting at 0. Is that going to screw it up? I don't think so. Yeah, something's fishing about this. Maybe you don't get it back. So if we scale this by z, you get az. It does not satisfy this functional equation. You see that? It's all messed up. Okay, well, what does it do? You could do this. You could like, this is the equation it satisfies. If I do z f of z, it scales everything up, right? You get a0 z, a1 z square, yada yada. There's no way to fix it. I was gonna say you could multiply by you could multiply this by a1 over a0, and you could multiply this by a2 over a1, etc. But it doesn't give you this. You're gonna have to, that's a weird formula, what I just said. If you want to get f back from this, I don't know, good luck. You're gonna get, you can't. You have to change every single term independently. You see what I'm saying? So I don't have a functional equation for just a general power series. It's not like I can just go, a0 plus z fz equals fz or something. Yeah, you see what I'm saying? There's no fixed scalar inside this that would fix all the coefficients. There was for us. That's, we happen to get this recursive thing, this functional equation. But for a general power series, I guess I'm going to say no. My instinct is that you won't get a general formula for the reciprocal of a power series. We were about to, because we had this functional equation, but we definitely don't have. It looks so close. Not really. All the coefficients are different. When you multiply by z, you've sort of shifted the coefficients, right? And I just don't see a way to get them back. You can't. There's no scalar that you could put here that will suddenly shift them all back into place, except for 1 over z out front. You know, if this wasn't there, then congrats, you get your series back. But yeah, huh. All right. So power series, no functional equation, at least in general. And this is still kind of open for me. Is there really no power series representation for the reciprocal of a power series? It would be nice if there was. It's got to be something. There is for, it depends on the function, right? Like there certainly is for E. I mean, that's an obvious, E is analytic, right? Yeah, if you're an entire function, then, No, that doesn't really answer it either, right? What about something like sine? This thing has no roots. That's why that worked. Its reciprocal was also analytic. So sine of z has a power series representation, but its reciprocal has a bunch of poles. Okay. So this one works, this one does not, I believe. I haven't thought about the reciprocal of sine, a power series for it, but I imagine it doesn't really work because it would have to stay away from poles. You know, this radius of convergence that you get for this function is certainly not the same as the original. But that wasn't a condition I needed. I just wanted a formula for its reciprocal based on the original. I still think there might be something there. I'm not saying the radius of convergence is the same, but that's sort of, you know, that immediately leads you to say like, well, you get a totally different series, so. But yeah, I still wonder, is there a relation between these two in general? Anyway, let's wrap up number 51. He probably wanted us to find these coefficients, but I've found that this is true. So what? Well, okay, so write out your series. So on the left-hand side, we have this, and on the right, we have this thing scaling. Don't do that. Use this one. Okay. Sorry. We have this times 1 minus qz equals g at qz. So on the left, we have regular series starting at 0, I guess. And then minus qz times that same series. So the z kind of scales it. So let's pull this number out. I'm always confused by that constant term. So we have b0 plus the sum from 1 to infinity of our series. And then what we're subtracting is q times, well, I'll just do it one step at a time. We scale that up. And then on the right-hand side, we have our series, but instead there's an extra q to the k, z to the k. So here's the stuff on the right-hand side. And on the left, again, this starts at 1. No, it starts at 0. But when we reindex, you know, we could start at 1 if you want and change this to a b minus 1. So if we reindex this, you're going to get b naught, 1 to infinity, bk minus q bk minus 1. And that's the, this formula is identical to this formula. Like, these are the same. These are equal. So bk minus q, and what happened to my, oh, I multiplied by qz. That's what happened to it. So you no longer have a zero term here? No, you don't. What happened to the b0? Oh, is this wrong? Is this minus 1? Yeah, this is wrong. This is supposed to be a minus 1. It started off as b0 plus b1z, right? Etc. And then I multiply by qz. So I get q b0 times z plus q, not exactly. It's of qz. It's not multiplied by qz. Okay. So this is wrong. So b0 is still there. Okay. So it is 0. Good. Okay, fine. This was fine. So there's still 0. All right, cool. So let's pull the 0 term out. We get b0. So from 1 on, you get a statement like this junk is equal to bk. And we can use that to solve for bk. All right. What the hell's going on? Why did it fall apart? Clearly I made another mistake. Oh, I forgot the q. Duh. Good. That makes more sense. So yeah, add, subtract. You'll get, bk times 1 minus qk equals this. You can divide do we have a comment on what b0 should be? Oh no. I mean, I remember from the previous discussion, I'm not going to be able to get it from this functional equation. But also it's the reciprocal of this. Man. Well, at 0, you just get 1 again. You get 1 over this stuff. So it does stand to reason that b0 is 1 again. G of 0 is 1 over f of 0, which we know is 1. So this is okay. b0 is 1. What were you doing with this? Were you going to finish this up? bk is given by this formula. Oops. Damn it. Sorry. It's given by this formula, which, again, oops, did you miss a k? Yeah, you missed a k. There it is. Which, I guess we could iterate and see. There's an explicit formula just like there was for number 50. I don't think I didn't prove it by induction or anything for 50. I just observed what the pattern would be. Here's what I mean. On 50 a minute ago, once I got that formula, I started jotting down, and I noticed, like, of course, every time you multiply by the next power of q, so you're getting 1 plus 2 plus 3 plus 4. So you get a formula upstairs like that. And then downstairs, you get repeated powers. I wasn't going to expand this and see what you get. Yeesh. But he didn't want us to. But here you can do the numerator again. Why is it the same numerator? It can't be the same formula. I got this. What? How's the same? Oh, it's not negative this time. That's weird. It's the same formula, but with the denominator flipped. It's like, it looks like it's the same formula, but there's a -1 floating around. And downstairs, you just get a bunch of these powers. Well, here, like qk -1, qk -1, -1, all the way down to just q. It's the same as the AKs, but with a negative in the way. I don't think I made a mistake. Subtract the qk, I got that. Add this, I got that. So I'm right about this. And anyway, weirdly, it's the same formula, except without a negative sign. I had gotten the negative of this for the a's. So when you iterate it, if you insist on putting the q out front like this, I don't know why you would. It's actually, this makes more sense. Like, this is positive. Anyway, it's this, or if you don't want to do this screwy thing, it's the same as this, but then downstairs you get 1 minus q, 1 minus q square, up to 1 minus q to the k, like that. I'm not sure which way he's going to put it in the book. 51, according to blah, we get this, therefore, yeah, he left it as 1 minus q. In AN, I had changed the order because I didn't like the negative sign, so I put the q out front. But for the BNs, you get, oh wait, my numerator's wrong. Huh, I'll look into that. The denominator's fine. The numerator, he's saying, and of course B naught is 1 again. Yeah, he's saying my numerator's wrong. Why don't I mean, I just skipped doing the work, but why? How could it be wrong? Q to the k. Yeah, this is the right-hand side. This one gets scaled once. Yeah, that's fine. QBK. Wait a minute. No, that's right. This one has it, but this one doesn't. This wasn't supposed to be there. You see me correcting stuff that wasn't there? I saw this and was like, oh, Q to the K. Put it there. Nope. Okay, so this is wrong. If this is just a Q, then every time we do it, we add 1, and by the time you get K, you get Q to the K. I see. Good. All right, I see. Oops. Okay, so that is a different formula. That's weird. That is a different formula from part 50. I'm going to skedaddle onward. 52. What's 52 say? Hey, we've moved a page. Yay. All right, what does 52 say? Determine the coefficients in this identity. Oh no. So it's odd powers, and then you're also taking reciprocals. And why would I mean, I guess it stands to reason it would be symmetric. Yeah, of course it would be. Okay, fine. So again at 0 you get C naught, and again at 0 you get 1. Wait, I can't plug in 0. This is a weird series, man. I can't even quite use the previous, right? Because 50 involves q squared. It involves all these even powers, which for some reason are not here. Well, if you can I factor this? If I factor all the even powers, no, you're still going to get some even powers. Yeah, it doesn't look the same, but okay. There must be some functional equation for this guy too, but I just don't see yet. If we plug in like qz, you get q squared. All right, so if I plug in q squared z instead, oof, no good, right? Because these reciprocals screw it all up. All right, what if I instead look at separately product of odds, you know what I mean? Like, let f be just the regular series, no reciprocals. How did I screw this up already? That's a 3. This is not there. Okay. 1 plus, there were pluses. 1 plus q to the 5z, etc. I wonder if I could do like 2 separate ones. Well, you know, just do this. I wonder if I can get like a, yeah, like this is the same as fz. It's true, but so what? Like, am I going to be able to use this to get coefficients for this guy, and then use the same coefficients for this guy, of course, and then just multiply the two? You know, if I had, here's a formula for f, it starts at 0, and this time I do have f of 0 as 1. And then here's a formula for, well, isn't it the same? Yes, it's the same, but then you can't use a nice formula to combine the coefficients. Well, okay, so it's this. And then, you know, what I get is a bunch of different terms. We have to talk about that to see what powers you get over here. But you do get a power series, of course. But that's also not quite what he said he wanted. He wants a sum. Like, he's saying it's going to be symmetric. Just give me the coefficients. But okay. I mean, that's not a problem. This I feel like this should still work. So like when this is 1 or 0, you know, the first term gives you a whole bunch of terms. Actually, there's a lot of interactions. it's gonna be the same kind of formula, like I was expecting something like product is a 0 bk, a 1 bk minus 1 up to a k b naught. It doesn't really work anymore because that's not the way that's just not the way it works. It doesn't work when this is not the same power. So no. But something like that. I should be able to say, you know, you get z to the m where m is k minus j, and you know, we can fiddle with that. But this all hinges on me using this functional equation to get the coefficients for f. Hoping to make more progress today. We really only did 2 problems so far. This is a neat idea, but I mean, what's your follow-up here? What's the rest of what you were going to say? So call this J, and of course this is not actually shouldn't this work? Shouldn't I, if I'm using this as the power, shouldn't I now just be able to do this formula again? Not really used to messing with these. Anyway, this doesn't matter. No, you probably don't get the same exact formula, but say m was like 1. You get all the pairs where this is true. There's an infinite number of them. Oof. But you know, big deal. So you just get the pairs AK, AJ, where, you see what I'm saying? Cm is the sum of AK, AJ, where, well, k and j vary, like k and j go from 0 to infinity, but also this is true. K minus j equals m. So that's the sum that you get. If you want to write that as k minus m, you can do that to get rid of the j, you know. Yeah, there's only one at a time. I know I wrote this, it almost looks like it's a double sum, but it's not. It's, so what's the smallest? Yeah, the smallest k index is just 0. So I think we can just do this. K minus m. Wait, what? K minus m is j. This feels very weird. Oh no, is that not what I meant? Don't you normally add these? But we're not because this is the reciprocal. So yeah, it's fine. That's why that's backwards. That's very strange. Okay, well. Also, doesn't it stop making sense at some point? Like once you get to m, you can't go to m plus 1 because these are, so this is actually finite. I guess we're claiming that this stops at m. There's no reason to look at k being m plus 1. Huh, strange. Well, that would be my approach. And then I never got the A's, so let's think about that for a sec. Just write out the sequence again, just like we've been doing. Write out the series. So right-hand side, you just get these. Left-hand side, you get these scaled by q squared in every single, every single term. So left-hand side looks like, yikes. Right? So left-hand side is this. And we'll clean that up in a moment, hopefully, and then again, it's going to be easier for me to pull out the constant, probably, right? So this is a naught plus the sum of from 1 to infinity of even power of q. Anyway, and then what? qz times this mess. Yikes. Anyway, the right-hand side is just the original function. So the right-hand side is just ak z of k. There's a scaling that goes on here, right? You still start at 0, but so we still start at 0. You got to be a little careful there. All right, fine. So it's q to the 2k plus 1 and z to the k plus 1. And we should reindex this so it's starts at 1. But this is then ak minus 1. This is then q to the 2k minus 1, right? Yep. And this is finally fixed. So that's our second term. That's this stuff times qz. So I'm going to write that here. So we've got the same, we can match the coefficients up now on the left-hand side. That's okay, I guess. We got an even, yeah, we'll ignore a naught. But for the rest of them, I mean, of course, they're identical. A naught is a naught. For the rest of them, we're getting a formula like even power of q ak plus, let's say, previous value of q times ak minus 1, right? Something like this. Q to the 2k ak plus q to the 2k minus 1 ak minus 1. So there's a sort of recursive expression for the ak's, which we could solve. And then I thought once I had that formula for f, right, I could then just take f of 1 over z to get the others. Remember, we're looking at 52 here. Oops. We're looking at 52 here. So I basically said every other term, the ones with like positive exponent for z, or the ones that aren't reciprocals of z, that's 1, 3, 5, etc. 1, 3, 5, etc. And then I noticed it had this, it satisfied this functional equation. Notice there's a q squared there so that you always get odds. Anyway, I used that to get these coefficients, which I didn't finish. I didn't get a closed form yet. But then for the other factors, I looked at f of 1 over z, which is of course the same. That's fine. There's nothing wrong with that really. And then he wants me to find c's in front of this, basically make a power series out of it, right? And he's clearly observing that it's symmetric. I didn't think too hard about that. I just said, all right, well, you take the product of these two, you'll get a new power series. The power m coincides or corresponds to k minus j being m, right? So when you take this product of these two sums, I'm more used to doing that with a positive exponent here, but not a big deal. That's why this is a minus j instead of a plus j. But otherwise, you get the same kind of formula you always do when you multiply these guys. When this happens, you'll get ak times aj. And of course, j is k minus m. And also, I'm assuming that the a sub negative thing equals 0, like a sub k equals 0 for negative. It just goes without saying. So that's why this is a finite sum. I don't know if we have anything else to say about that. It doesn't even start at 0, right? It would have to start at like m. That doesn't make sense. What? They have to both be positive, right? So like 0 is okay here, but I'm a little lost on when this makes sense. Like what if you're at, say, C3? You get nothing until you hit 3, but even then we stop. Like this formula makes no sense, what I wrote down. You get one term? I mean, I just get one term. It's like AM. You just get AM A naught every time? You just get AM? What the hell? That can't be right. I knew this was going to screw me over at this part. I don't really see what I did wrong, but I didn't think very hard about it. I guess we could write it out. Well, yeah, what would be wrong with this? Because you also get, like, if j is 0, you get a term. How could there be no terms except for the 1? There's a bunch of pairs. If this was like z squared, every time that the difference is 2, I should get another term. I was expecting kind of an infinite sum, right? For z squared, you'd get like a2, a0, a3, a1. Yeah, of course you do. So that's an infinite sum. Maybe I was thinking about this really wrong. This is fixed. Why was I flipping out about this? Yeah. This is wrong, what I said here. But this is still true. For some reason I thought this would become negative, but why would that ever become negative? Once k is bigger than m. Yeah. I just read this backwards. Okay, shut up about this. Shut up about that. That's not true. But this is okay. This is exactly what I wanted. Yeah, for some reason I think I read that backwards. I thought it was m minus k. And I started to like cancel the terms. But yeah, k minus m, no problem. They both go up, and every time you have a difference of whatever m is, you're going to get another coefficient. And yeah, I can't change that. I can't simplify it. But that's fine. It's an infinite sum as it should be. Yikes. Yikes, man. Yikes. This is clearly not the way he did it, right? Anyway, let's finish this up, get those coefficients, and then I'll see what he did for the answer, because I don't know what else to do with this. I thought my idea was like pretty straightforward. He's also saying they're symmetric. Yeah, they would be, right? You just do the same thing, going the negative direction. But shouldn't I have infinitely many more? Well, this stops at 0. That's why I'm stopping at 0. Okay, that's fine. Yeah, that's fine. All right, fine. Let's get these coefficients then. So subtract, and so you're getting something like ak times 1 minus even power of q is the previous odd power of q times ak minus 1, right? Just subtract. You can then divide, and we can probably iterate this to get you a closed form thing. So here's our recursive relation on the coefficients. And if you want, we can, I mean, I need to really write a few out to see it. I'm not good at doing these just in my head or something. Well, you're going to be adding odd numbers. On the top, you're just getting this times this times this times itself, right? A bunch of times. So downstairs you get, like, say you started at 0, you don't get anything. That makes no damn sense. So we're assuming that a0 is 1. Don't try to use this formula with a k equal to 0. But at a1, you get 1 minus q, you get 1 minus q to the 2 downstairs. So if you have it k times, you get this kind of business, k times, right? And then upstairs, you do get a sum, but it's a sum of odd numbers, which I should know off the top of my head, right? Is that going to be a square? If you add up a bunch of odd numbers, you get 1 or 4 or 9. The sum of these, I mean, I hesitate to call them triangle numbers, but they're square numbers. The sums are square numbers. So at, say, 1, you get 1 squared, right? You're getting k squared is what I'm saying. At 2, you'll get 1 plus 3, etc. The infamous square numbers. Anyway, if you look up something like the sum of odd integers or whatever, that'll probably get us a formula like that. So I got this for half of our function, and then I got a product like this. Now I'm kind of curious what his answer was for 52. Appel and McCord, 1897, and Gauss did it. Calfien, the exact expression, we get this identity. Huh. Whoa. Looking at 52. Yikes. CV is this mess. Okay. So yeah, he did a recursive, or functional equation just directly. What was mine again? Like 1 plus QZ. Huh. Yeah, I didn't do this. I didn't try this at all. 1 plus odd Q over even Q. I mean, obviously I got that pattern, but all right, whatever. From this identity follows, and then he gets this relation, which is similar to what we had done. He uses this to solve q to the n squared. I don't actually see. Oh. I see. He's getting both of these. I see. I was like, how does this simplify to that? It doesn't. He's saying for the first n terms, you get this relation, and then for the nth one, you get this. Also, what is phi n exactly? Oh, it's supposed to stop. I didn't realize it was finite. I see. I just went on forever. Yeah, sure. So if you stop, then you could probably figure out something. Let's see, if you stop at like, what is it supposed to be? Q to the 2n minus 1. Yeah, we get both of those terms. Well, he calls it phi n. I would have called it, well, mine I would have to truncate mine. Mine was an infinite series version. 1 plus q, yeah. Two n minus 1. 1 plus q 2n minus 1 is e to the negative 1. Yeah. So if I saw this and I wanted to make a recursive relation, of course I would just go, I would plug in q squared z. There's kind of a problem with that, isn't there? No, there's not. Well, yeah, there is. What the hell? Like, this gives me the next, but it screws this up, doesn't it? It gives me 1 over q, which was not even part of... Do I have to divide by it? It happens again and again. Is that really his relation? You're dividing by like a product of 1 plus reciprocal of q. Huh. Okay. Maybe. Alright. Q squared z is the right idea, but... so once you do this, you're going to be missing the first term. So of course you have to multiply by 1 plus qz. But you're going to have to do more than that. Yeah, get it. Q squared z in here screws up my q. Right? Although it only does it a little bit. Oh yeah, wait a minute. Yeah, it's doing something funky. Q squared z, it gives me that one. Maybe just write them out, okay? Phi n q squared z gives you cubed, and then here it gives me, well, it gives me q minus 1. Yep. Okay, fine. And then here it gives me 5, but here it actually gives you back something that was there. Wait, not 3, but 1. Right, 3 minus 1, so 1. So that guy's actually still there. That's interesting. On, and then over here you get like 2n plus 1, which is not supposed to be there. And you get qn 2n minus 3, which is there. So we're missing the first guy, of course. I knew about that one. But we're also missing 1 plus q 2n minus 1. Like we're missing that factor. And the extra stuff that we got was this guy and this guy that are not supposed to be there. And that's it. It's not as bad as I thought. So obviously multiply by this, divide by this. If you expand this, I wonder if you'll just get exactly what he wrote in the denominator. Ugh, Jesus. What the hell? So this, inside term and outside term looks like this odd power times z. Wow, that sucks. And then this stuff, I don't know. Why are we bothering to do this? You get 1 plus q to the 2n, yep, plus qz plus 2n minus 1 over z. Yeah, sure. So that's your relation, right? Like, it's this divided by this stuff that it contains. Yeah, that's not wrong. Is that what he said? 1 plus q to the n plus 1z. What? That's not what he wrote. Q times. Did I mess it up somehow? I don't think I'm getting the same thing. So he's claiming that it's supposed to be, Vn z times. So he's claiming it's 1 plus q 2n plus 1z over qz plus q to the 2n. Right? He's getting this. Then he uses that to get some identity and yada yada. So what I thought for 52 is weirder looking. It's also up there in the corner. 52 says we have a different function, first of all. It's only odd powers of q, and also it's involving reciprocals. And I kind of misread it, and I thought it was an infinite series. But what I decided to do was like the same approach, like let f be this function, but just with the positive parts, no reciprocals, and then let g be the same function, but evaluated at 1 over z. And then I was able to get coefficients. I was able to get a formula for that f that I invented. And then I said, all right, I'll just take the product of f and g. And that was it. And I got an answer for the CMs. It was kind of nasty because it's an infinite sum. I was supposed to be finding these coefficients, but what I found instead was like the product of, like, here's a formula for AK. And so my coefficient would be an infinite sum of AK times AK minus M. You know, if you want C1, it's AK times AK minus 1, right? But instead, what he had done was he just directly got a recursive relation. He made a functional equation out of this nasty function in 52. You can look up here again for the function. But yeah, he got this functional equation, and then he gets the answer. Like, he went from there to pretty much doing the same kind of computation that we have been doing, and he just immediately gets those coefficients. But I'm like, how did you even get this relation? Because that's not what I got when I tried to do it. First of all, I didn't do it that way. But even trying to do it his way, like if I just look at the original function, I get this as a recursive relation. I don't get this nice thing. Anyway, we're in pretty deep, as you can see. It's craziness. And I wrote down, I'm supposed to get this. Really should screenshot the answer, huh? I'm supposed to get this, but instead I had gotten like if you do q squared z in this original function, you get all the odd powers back. You get one extra odd power. Oh, by the way, I'm doing it correctly now. It wasn't supposed to be an infinite series like I had. It was supposed to stop at n. But okay, fine. So stop at n. And what I got was this as this functional equation that we're supposed to get. But he's saying it's this. So like apparently this divided by that is equal to this stuff. I just didn't see that happening. You know, these are supposed to be the same relation. This is the one I got, and this is the answer. I don't know, man. I don't know. I mean, I started, so I just did some naive, you know, I multiply these out. I get this, you know, the product of these two binomials. So yeah, apparently this junk is this divided by that. This numerator, this denominator gives you this. I'm just not seeing that. I haven't really thought about it very hard, but I would not have guessed that it was this, you know. Anyway, even if I knew that was true, he then gets these. I mean, that's not too bad. You would just write out the left and right hand sides. So clearly this falls out from the previous functional equation, but you know, wow. then he goes on to actually solve it in general, which looks crazy to me. But I was feeling really good about my answer, you know? I had gotten like this. I got the square thing. I'd gotten this basically times k minus m, you know, so I'd have like this plus itself however many times, like n times, and you take this times the same expression but at k minus, say, 1 or 2 or 3. So kind of an unwieldy expression when you do it my way. But when I do it his way, I don't even see how he got this functional equation. But yeah, so that's what I'm up to. 50 and 51 were really not bad. You just sort of, once you get that functional equation, you can jot down the series on the left and the right hand sides and just equate the coefficients, and a formula pops out, and you're done. So he's trying to get me to do that with this one too. But yeah, I didn't think to just attack it directly. I thought I was being clever by splitting it into the, splitting it into, where the hell are we? The regular ones and the reciprocal ones. And I was like, well, I'll just take the product of those two. I'll do them separately, and we'll see what happens. And I got an answer that I suppose is a little gross. But now that I see his answer, I'm starting to like my answer more. But my answer was maybe not complete, so that's what you get. So I don't think I'm missing anything. One thing that was annoying is when you plug in q squared to this reciprocal, it divides by q, of course, and so you get this extra term that doesn't belong there in the original function. But the other ones do. QZ is there. Yeah, wait a minute. If QZ is there, I didn't even notice that. Fuck. This is not there. This is not missing. I didn't even notice that. This is not missing, which means probably this is not missing either, right? 1 plus q minus 1. No, this one is missing. I don't know how I didn't just notice that this is still there. So you're not missing 1 plus qz. Never mind that. So what else is not missing? Am I containing? Did I write something down that it doesn't contain? Yeah, this is not supposed to be there. But anyway, you plug in q squared z into this original function. You get a cubed. You get this guy, which is not supposed to be there. That's why I wrote it here. And then you get to the fifth, which is supposed to be there. The rest of these powers are fine except for this extra one. This extra one, which is not supposed to be there in the original series. So I got two things that are not supposed to be there. And for things that are missing, for some reason I thought this was missing, but I guess that can't be right. I think I forgot to put a reciprocal here. That's why it is still missing. Yeah, this is a reciprocal. So shut up about this. This is still there. This is supposed to be a reciprocal. But that was this guy. Okay, good. So this matches up with that. The next one will be q cubed. That'll be there too. So now this is still missing. Yeah, I don't get how he gets this in the numerator. My series is missing 1 plus qz, and it's got an extra of this. It's also got an extra of the last term, and what the hell is this? No, this is already there. This was there. But you're missing 2n minus 1. This guy. You're missing that. So I think I'm correct about this. This was fine. What I put here is true. Anyway, so I would have had this relation that I wrote up top. But he's saying it simplifies to be this. And I just don't. I don't know what you're talking about. I guess I could try it. Like, what if I multiply the top by qz? I mean, what if I multiply the whole thing by qz over qz? You'll get qz plus 1. And upstairs you'll get, like, I don't know. I guess you should put it here. You'll get this. Well, not quite. All right, so if we take mine, which I believe, I understand this one. I understand mine. I don't quite get, I'm supposed to get this. Anyway, if we take mine and we get rid of these reciprocals for one thing, so scale it by qz over qz to clean this up. That'll actually take care of this as well. So let's go ahead and do it. Qz over qz times this right-hand side. Let's put it this way. 1 plus 2n minus 1z, 1 plus qz. And then downstairs, I'm going to go ahead and leave this nasty bit out front because it's going to cancel in a moment. And leave this part. Sure. So anyway, when you distribute this, well, you only apply it once. It's this times these two other factors. But when you distribute in here, you'll get qz plus q to the 2n plus 1. Damn it. Did you forget a... You clearly forgot a... Yeah, good. So z times z reciprocal is gone. This is correct. We still have this other term. Oh, is it going to cancel? Dave, you fool. Of course it cancels. So he is right. It simplifies. Okay. Cool. So these are gone. And you get... What? Well, did he factor a z out? Multiplied by z? What? So these are gone, right? qz plus 1. Fine, good. So these are gone. So my answer has now become q squared z. My answer has now become this. You could factor a q out. Oh, this is gone. You could not really factor a q. I mean, okay, I get z plus q to the 2n. I don't really want to... I'm confused. What? I said I was missing left-hand side, right? When I put a q squared in, it keeps giving you odd powers. So you get the 1 becomes a 3, 3 becomes a 5, etc. For the reciprocals, it subtracts 2 from the q's. So you get this weird extra guy. But the rest of them actually match up with what's already there. On the tail end, you get an extra 2n plus 1, and you're missing this guy, q to the 2n minus 1. So what I wrote down here is true, and that's what I put in my relation. Like these are the terms that are missing. Like you want to multiply by these missing terms, and you want to divide by these extra containing terms that I call them. So that makes total sense to me. And then to clean up the reciprocals, I don't know how I didn't even notice this, but if you just multiply by qz over qz, you're getting qz plus 2 to the n plus 1. And then downstairs you get qz plus 1. So these actually cancel, and I'm here. And he doesn't have I didn't write it backwards. Why does he have an extra q downstairs? it's like I just don't see what he's doing. But I'm really close to it. Like you can see how like I'm like circling it. Why, this is not the same as what he wrote down, but it's like close. I have this. Did he maybe evaluate at Z reciprocal or something? Like what are you talking about? Did I write down, did he put a reciprocal in? No, he didn't. He didn't. Did I write it down wrong? No, I didn't. Okay, so this is what I'm supposed to get. Anyway, what I do get is this. So now the question is, at least, is this the same as this? I mean, could multiply by z over z or something. Like, I'm not seeing it, man. I mean, you could factor q out, right? And it cancels. Like you could, but then I get this stupid reciprocal of q. Like that doesn't help anybody. I get this, which is not at all what he has. And what happened? No, I don't get it. Did I screw this up? Oh, sorry. I screwed that up. That's a 2. That's a 2n plus 1. Why are they the same? That shouldn't be true. Why are they the same? Damn it, Dave. Why are we being sloppy? Yeah, what are you doing? That's a 2n. That's a 2n. Man. Alright, so did you factor a q out or something? Whatever. You're going to keep making mistakes. It's going to be very difficult, man. Alright. QZ... Yeah, I think I see why I did that. I thought it was q squared. Okay, fair enough. But that's 2n, is that numerator. Oh, well, in that case, do you think he just I don't get it. Huh. Well, at least we got somewhere. Like, is this true? QZ, q squared, q to the 2n. And then down here I got 1 plus odd QZ. That's this guy. Which came from me trying to remove this containing term, like this extra term that popped up when we scaled by q squared, right? When we scale by q squared, it in the reciprocal part, you're dividing by q squared. So your last term looks like this, which was already there, but you're missing this guy, so we multiply by it. That was where this came from. We just eliminated that guy by scaling by QZ. It became this instead. All right, fine. But yeah, why would this be the same as that? Man, I got a lot closer at least. So divide by z. I can't divide by z, that's not going to fix it. This is not a reciprocal. Man, I thought my approach was really elegant, except then I ended up with... Sorry, I have ADD apparently. I really liked my approach. I was feeling very clever that I would just look at half the factors, and then this would take care of the other half of the factors, and I get a product. And that's a pretty standard thing we deal with, especially in the last couple pages. And then I even got a formula for the AKs. But the problem was then I'm looking at an infinite sum like it's actually not infinite. I didn't realize it was supposed to stop at n. So these stop at n. But whatever. I get a series like this, ak minus m, right? So this formula, so I get like qk squared times qk minus m squared. And then downstairs, and this is going from 0 to infinity. And then downstairs you get this, and then you also get the same product, but with k being k minus m. And so you get a bunch of overlap. So yeah, downstairs I would have had 1 minus q squared up through 1 minus q to the, well, I'll tell you what, we'll keep it simple, to the 2k. And then you also have the other factors coming from this ak minus m term. And there you'd get the same stuff, but it stops at 2k minus 2m instead. But again, this is a sum, which is a little bit unwieldy. Yeah. It's certainly not as nice as the answer he gave. Which I didn't write down, by the way. The answer he gave, once you justify this recursive relation, this functional equation, I should say, you get a recursive statement about this coefficients CV. And then if you solve them, you actually get a weird closed form thing. See, it involves the q to the v squared. Yeah. Anyway, so it's a neat problem. It's clearly the same approach as the previous ones. It's just a little gorier on the details, sort of from the get-go, frankly. Because I wasn't used to dealing with these reciprocals in the middle of the function. So as you can see, I scaled by q squared. That was normal. That was natural to do. Putting a q squared next to your z, that makes sense. And it gives you back, it gives you back this stuff. So it catches q cubed and q to the fifth, etc. But it introduces this stupid guy and this guy. Wait, no, that guy was there. Introduces this guy and this guy. And it's missing the last reciprocal term, and it's missing the first, this was not it, it's missing the first non-reciprocal term. So I fix that by multiplying and dividing. I get a statement like this. And if you bother to do this, you can see that this cancels. That's good. But I'm here. Right? Do you believe me? Well, I'm here because I canceled a q out. I factored a q out on top and bottom, which is kind of stupid. It doesn't look very good. So I'm here, say. And I'm supposed to get from here to there. But I still don't see that. Like, shouldn't I just be able to divide by q to the n and get exactly what he has? But I don't. Was this a negative? No. Better not be q to the negative. Nope, it's not. It's positive 2n plus 1. Supposed to get this. So yeah, if you factored q to the 2n out instead, right? If we factor q to the 2n, or I'm sorry, that's not what I meant to like divide by q to the 2n everywhere, but we're just going to get a reciprocal again. I'll get this'll match, but nothing else will. The 1 will match as well. So we could do that, but it's going to be wrong. So if we, do the same trick, you multiply by q to the negative 2n on the top and the bottom here, you're going to get, you're going to get 1 plus q to the negative 2n. It looks like that. And then downstairs, you get, well, let's write it as qz, because that's part of the reason I'm doing this. But here, you don't get that. You get q to the negative 2n. Man, it's like really close, right? It's almost the same, except that I have negatives here and here. This is what he has, except that he has he has positive 2n in those two locations instead of negative 2n. Q is a fixed, I can't it's not some arbitrary number. It's given to you ahead of time. It's a fixed number less than 1 in magnitude. Man. It's not like I can take its reciprocal or something. Plus, this is the same as that. So, what other trick could I possibly do? How did I... Oh, well. I don't know. Yeah, I don't know. As you can see, I thought I was being clever with my little multiply the series trick. But I suppose this is better if I ever got this to match up. Why would it? You can't just ignore this power. So, I mean, did I make a mistake at the outset? I don't think so. But I could have, maybe I'm missing like a single negative sign that accounts for everything, right? Or I'm pretty sloppy. Maybe I wrote down the wrong power up here somehow. I haven't really gone over it very well. I know I'm missing the first term, this guy, the first factor. So I wrote that there. And he carried over to here. And we want that because it canceled. Well, whatever. So say it's missing, sure. And then the last one, you get an extra one, like this guy. It was 2n minus 1, but I multiplied by q squared in the z, and that's why I get 2n plus 1 right there. Oops, sorry, right there. This is normally not the right term, so I mentioned that we're containing that, and we want to divide by it in my formula. If we divide it out, it'll no longer be there. We want to replace it with this guy, which didn't show up. He was there initially, but when we divide by q squared, by plugging q squared z in for this reciprocal z business, so when you divide by q squared, that becomes this, which is one of the terms. It's supposed to be there, but that means that we're missing this term. So I multiplied by it. So there's nothing wrong with what I wrote. Like, these are missing, and these were gained. This was not supposed to be there, but when you scale, it's the first reciprocal term that pops up. That thing's not supposed to be there, so we divide by it. And then this guy is also not supposed to be there in our original series, our original function, I mean. That's not there, so we divide by it. So I'm right about this stuff. I don't think I'm missing any more. And plus, that was pretty simple. And like, so okay, we're here. These are what we multiply by. These are what we divide by. Sure. I scaled it so that the reciprocals go away. If you do that right, you add a q here, just one q. You get qz plus q to the 2n. Yep. And downstairs, you get qz plus 1. Yep. Cancels, gives you this. And then you could maybe make it look like this by doing what? I mean, there's a z here, so you could multiply by q to the 2n. That's weird. That's not what he did. Sometimes I get there and I'm like, is it a typo? But I've yet to find a typo in his answers. Sometimes I'll be like, oh, I've got to be right, but I'm not. He's right. Anyway, even if I had that, I then have to write down this formula, write down this formula. Well, really, it's just the series times whatever, and then equate the coefficients, and this should pop out. I guess we could verify that next step, and that would demonstrate whether there's a typo, but I doubt it's a typo because it happens on the top and the bottom. I don't think he missed a negative sign in both places. Anyway, I got here. I was able to show that this is true. This stuff. And then if we divide by q to the 2n, you'll get this statement. You'll get this in the top. You'll get this in the bottom. I can't really argue with this. This is what I'm getting. And he's telling me I'm supposed to get this with positive 2n, not negative 2n. Wait a minute. Is it symmetric? And maybe that's the, no, that doesn't make sense. Because these n's are all positive. The n represents where we terminate. It's not like there's a negative n. There is no phi negative n. You know what I'm saying? Why not? What would be wrong with there being a phi negative n? Well, nothing, I guess, because this stupid function includes reciprocals. But there's no way that he... You sort of see what I'm saying? I could let n be negative 1. Wouldn't that be stupid? You'd get negative powers of q, which is not... That doesn't make sense. That's not allowed. Yeah, stop thinking that. That's not what we're doing. So yeah, n can't be negative. That doesn't make sense. N represents like how many factors we take. If n is 1, you just take these. If n is n, you get this many. It's 2n minus 1, well, from each set, from z and from reciprocal z. Anyway, back to the annoying... Well, I don't know. His answer differs, and I'm just off by a negative sign, somehow. But if we believe him, and we just move it forward, maybe we can finish the problem. It looks pretty gory, frankly. 2 to the nz is supposed to be the original times this stuff. The original times, what was it, 1 plus q to the 2n plus 1? So odd power q, and then you're dividing by qz plus q to the 2n. Oops, q to the 2n. So I'm supposed to, anyway, if you believe this, then it means that our power series, well, he's calling it C, isn't he? Yeah, he calls it C, first of all. He also, he immediately like notices that it's symmetric. In the question itself, I'm saying. If you look at 52 right here, he wants us to express it as let phi n be described as C0 plus C1 plus C2, etc. Anyway, I started to call it AK, but anyway, if we scale this by 2 to the n, you'll get yikes. Come on, man. Oh my god. See, this is why I didn't do it this way. What? Come on. Why would you do this to me? What the fuck? 2 to the n plus 1. Wait, what? Yeah, it's 2 to the 2n, right? Z squared, but you're squaring 2 to the n times z. So you're getting, yeah, 2 to the 2n. And you're also dividing by that amount. Ew. Whatever, you get the idea. C3. You plug in 2 to the n for z, you're going to get 2 to the n times 2 to the n times 2 to the n. Blah, blah, blah. And actually, this is finite. The largest power you'll see is z to the n. Did he write that way? Yeah, he did. He stopped at cn. So, okay, fine. We'll stop at cn. I get, this is going to be real confusing, isn't it? No, it's fine. 2 to the n squared. Does that make sense? It's fine. Anyway, this is my left-hand side, and it's supposed to equal, well, no question about it, is if you believe his functional equation, it equals the original stuff. Oh my god. This is madness. Times this function. How the hell? Well, I'm not verifying this. I'm just saying this is what would be true if we had gotten the correct. Remember, I had this with negatives here for the 2 ends. That's what I believe, but he's telling me it's supposed to be this. Okay, and somehow I can use this to solve Cn in general, but also I'll warn you, the formula is like this. So he didn't actually solve it yet. This is a recursive statement, involving the coefficients. He does solve it though. But yeah, he gets this as the follow-up if you were trying to solve for C's. This problem sucks. I really did not see this problem being so painful. A little note to self: when you see reciprocals, you should run far, far away. Yeah, so there's nothing to verify here. you set this equal to that. Although what is confusing me immediately is like, what happens to C0? C0 is equal to C0 times this. Really? I mean, it could be that C0 is 0. No, it can't. C0 is 1. It's clearly 1, right? I don't know. Is C not 1? Because there's a bunch of other terms that produce a constant term, right? Like QZ times QZ to the negative 1. So it's not necessarily 1. It's like it's a sum. It's 1 plus Q squared, right? That's part of it. Plus, I don't know. I can't really see. Yeah, there's a bunch of terms where Z times reciprocal Z gives you 1. So I don't know what C naught is off the top of my head. But we could also just plug in 0. It has to be 1, right? The function at 0. Oh, no, you can't plug in 0, dude. I said this earlier. Right. I can't plug in Z equals 0. So yeah, I guess it's plausible that C naught equals, like if you scale. So for example, one coefficient that you get is QZ plus Q to the 2n times C naught is C naught times the numerator. Okay. so what? Why is there a Z in the middle of my... Oh, yeah, why is there... Oh my god. Is there always a Z in the middle of my formula? What did I do for 50? For 51, I had... No, of course not. Yeah, why would Z's show up in the middle of this statement about coefficients? And why is this here? Like our recursive relation last time, well, it did involve Z. That's okay that involves Z. But then when I put it in the series, it like scales stuff, it changes the coefficients, and then that's what you equate. This is going to be but I can't plug in Z equals 0 anyway. I can maybe plug in Z equal 1 if you want. I actually don't even know what I can plug in, right? Because I don't know where this thing converges. But it's finite, so yeah, you can plug in whatever you want, as long as you don't plug in 0. Okay, so this is supposed to be an identity. We could maybe simplify it, right? But doesn't this already like make you a little nervous? Like, shouldn't I be able to plug in any power of Q and get... Does it give me the same statement every time, really? Let's see what it gets if we leave the Z there. What if I... 1 plus Q to the 2n plus 1 minus 1 Z, and then I should have put it here, minus Q to the 2n. Anyway, this is true no matter what Z is, but you can't plug in Z equal to 0. So this is Z. This is 0, really? 1 minus Q to the 2n. And I can't just... I'm not saying that equals 0, but I'm saying if you ever scale it by... Or if you ever... I can actually plug in anything for Z, any real number here. supposedly you'll get 0. How the hell is that going to work? I'm so confused. And this was just for C0, right? This was just me thinking out loud. No, this was the left-hand side. This was phi to the 2nz right here. And here's phi z, phi nz, excuse me. And here's the scalar thing that was part of his answer. And my answer was actually not much different than that. My answer had little negatives here, which is just as crazy. So I'd end up with this statement that like, this is supposed to be 0 for all z that are not 0. Oh my god, I hate this problem. What is the next one? You guys can see it on the screen, but 53, deduce the following from 52. That's our old function, right? Yep, that's our function. This is new. What is this thing? Anyway, it equals to this. Oh, okay. Wow, that's really interesting. Wow. Wish I was smart enough to understand this. This is a very pretty function here. We've got an expression for, I mean, when am I going to use this infinite product? But still, that could be useful if I was better at number theory or something. It sounds really, that's a really interesting result. Take a fraction and take squared powers of it. Oh, and it's also like a, I see, it includes reciprocals of z, unfortunately. So, okay, it's like a Laurent series, but you get this. Man, that's wild stuff. But really, how would I mean, the left-hand side is just our function, except he finally took the infinite series version of it. So I guess multiplying by 1 minus q to the 2n gives you just these coefficients? Really? I didn't take a close look at these coefficients because they were just so gory. I did see the square term, but oh, okay, there's your, yeah, that's what he's saying. That's what he's multiplying by, 1 minus an even power of, man, this problem is like warping my brain. I'm gonna have to think about this for a couple days. 53, he has no comment. Look at that, 53. Take the limit. Okay, what a jerk. 53, he just says, yup. Yup, just do what I said. Okay, if you took this and you multiplied by that junk, it would cancel out, remember it's every single power of 1 minus q to the 2n. So it would cancel out all of these just indefinitely. You'd be left with this weird mess on top, but then you get your coefficient. So I guess I'm still concerned there, like what are we going to do with all these? That's part of it. You don't just get this one term. Are these canceling somehow and I don't realize it? There are even powers of q, but like I don't get it. I don't really. This is our old function. That's the same as it was. Yep, starts at 1. And then he's scaling by this, which it stands to reason you just remove that from all the coefficients. But yeah, why would he only get the qn squared part? He's kind of ignoring this whole numerator for some reason. No, I don't see it. I don't see it. Oh, are these the rest of the terms? No, I still don't see it. I was wondering if there's some like cancellation happening. Like if I put in qn minus, yeah, eventually you'll get this, but I'm still missing some terms. So if I multiply on both sides by like all these even powers, and I just keep going, you will eventually, but you don't hit these right away. You don't get this immediately. We're missing some terms. If you multiply on both sides, these will cancel. The stuff that does not cancel, yeah, I still feel like we have some extra stuff in the middle between this factor and that factor that don't just cancel. Right? Aren't I missing like 2v? I'm missing like v terms. Right? This plus 2, this plus 4, all the way up to whatever this is. So you're missing like v, you're not missing v terms, you're missing like 2v terms. 2v factors, I should say. Yeah, I'm gonna have to think about, so anyway, if I figure out what the hell's going on there, that's 53. It doesn't look too painful, except that I don't have a grip on this coefficient. He also, though, he did say that Cn is this, simply, when you just have v equal to n. Maybe that simplifies it a lot. Maybe I don't have to think about this at all, somehow. Because the nth coefficient is exactly the right-hand side in number 52. Anyway, I'm making a mess of this today. I need to wrap it up. So we did 50 and 51 with no trouble, really. Those are pretty straightforward. 52 has been a nightmare. But somehow, I feel like there is light in the woods here. I'm still in the center of the woods, but like I can see that someone must have gotten out. So it's like tractable, just not by me today anyway. And 53 also, I could see that being an application of this. I still don't quite get it, but like maybe I can, I don't get it. Because like for any finite n, these terms don't just go away. Like the term looks nasty. And then for Cn in particular, you get this nice answer. But there's other terms there. I can't just ignore all the previous terms. Also, I kind of need them there because when you multiply by, where is it? When you multiply by this thing, those showed up in the coefficient over here. So like I kind of need them to be there so that I can just multiply. Yeah, well, I'll keep working on it. So 52, what else happened though? Did I get stuck on this? I think I like didn't want to think about this anymore. I got stuck here because this made no sense to me. This is just coming from C0. I don't understand how that could possibly happen. Like just take one. It means that, or we could even take Q. I just don't get how this could possibly be true. First of all, it's, like I was saying, it's a finite series, so I can plug in anything for z except for 0. So it's going to be convergent, and this is supposed to happen. And you're telling me that like q to the 2n plus 1 is equal to q to the 2n? Like what the hell is going on? This can't possibly be true. Then did I make a mistake? Or aren't we supposed to, no, we're supposed to scale it by this. I did that. This times C0. So I multiplied the denominator on both sides, and I got this mess. And on the right, I just got C0 plus this power, or this stuff times C0. So, I mean, I don't need to write it down again. I already did this. QZ C0 plus Q to the 2n C0 is C0 plus, I don't know why I'm doing this. Oh, times C0. Yeah, whatever. It's the same thing that it said a moment ago. I don't know. That's the same thing I had. Unless C0 could be 0. That would make my life a lot easier. Okay, fine. C0 is 0. Well, why? I mean, it's something. Like I was saying, it's actually, it's like 1 plus q squared. How could I add up a bunch of terms? None of them are subtracted. How could I get a series like this and have it end up being 0? Well, I don't know that this is the series. I'm just saying, when you look at the original function, whatever, where is it? It's like 1 plus qz, 1 plus q inverse, 1 plus q cubed, 1 plus q cubed inverse, etc., right? This is the function phi n. And I was like, oh, great, the constants, the coefficient is 1. But that's not true. That's not really true, because these cross terms do give you, but at least this is finite. So if we had phi 1, for instance, you'd be looking at 1 plus q squared is the constant term. Then you get other stuff. You get qz, I guess that's it. You get qz inverse. And you also get what? We already took care of that one. So that's it for phi 1. Here we get this. So yeah, that's what I was expecting to see, was a series like this. You know, like that. So how could this equal 0? I mean, it doesn't. It can't. Does this equal 0? No, it doesn't. Okay, fine. Sad face. So I still don't have an answer for what's going on here. He's not wrong. What if we do it my way? Does it make any more sense? No, my way doesn't make more sense either. Like, I have a negative here and a negative there. Right? In this formula, I'd be saying like this stuff equals 0, and I'd have like a reciprocal for q basically, and same over here. So mine would be a negative here. My one that's probably incorrect would say that, oops, forgot the 2. This plus q to the negative 2n plus 1 minus 1 equals 0 for all z not equal to 0. Still doesn't make sense. So even if he was miraculously wrong, both of us come up with a statement that makes no sense. All right, I don't know what's going on anymore. Clearly I forgot how to do math. I'll have to give up for the day. But thank you for all tuning in. I'll jot down a couple more of these. This function would look like, now we do odds, and then we stop, right? This is to the negative 2, or this is n equal 2. And you do get, yikes, you get a bunch of stuff, right? Pretty sure you get q to the 4, but I guess I haven't thought about it. Oh, no, you don't. Maybe you get more than that. Still, it doesn't make sense that it would be 0. Any more than this would be 0. Oh my god, my brain. Yeah, well, this problem's really complicated. I don't know why it's so bad. It doesn't look that bad. anyway, I didn't get his relation, and even if I had it, I didn't quite get his relation. I had like a negative sign. But even if I did have it right, this is the page where I had it right. I'm supposed to be able to just equate, or, you know, just, yeah, equate the coefficient in front of z to the coefficient of z over here. But that's kind of easier said than done, because this is nasty. So normally you would just multiply by this denominator on both sides. Here you get itself plus q to the 2n plus 1 times z times this stuff. So we do get some changes in the, you get some serious shifting going on, because now that these reciprocals are here, some of them kind of cancel. So it's a little weird, the shifting that happens when you multiply by z in this. Yeah, this problem is crazy. And I don't think I feel like expanding this. Don't think it's going to help me. It's going to be this times this stuff, right? But anyway, in conclusion, lots of confusion today. I'm going to have to disappear. Thank you all for tuning in. Thank you for the raid, Zach. All right. Take care, everyone.